This lesson is on assigning oxidation numbers, and this is skill number 1 in your electrochemistry or redox unit. In redox reactions or electrochemistry, which are synonyms, we are dealing with chemicals, in these chemical reactions where their oxidation numbers are changing. Now, even in covalent compounds, we will assign oxidation numbers, and oxidation numbers are the individual charges that we assign to these atoms that make sense in order for these atoms to be electrically neutral. So, going ahead, we have some rules, but a very important skill, because in a redox reaction, as you are learning in class, a redox reaction is broken up into the red and the ox. And the redox reaction, as we're going to learn, means that there is something called reduction. And reduction means, believe it or not, gaining of electrons. All right, and oxidation, or the ox, is oxidation, and that's an older name that we've used. It's an older name, oxidation, which means gaining electrons, and it comes from the action of oxygen, on other compounds. For instance, case in point, let's say we have iron, and let's say we have oxygen. As you well know, that with the exposing of iron to oxygen, we're going to make a corrosive compound, or at least a compound that is corroding from metal, I should say. So we'd say that iron corrodes, easy for me to say, from the action of oxygen. Now, we learned that iron, like most metals, holds on to its electrons a bit loosely than the nonmetal here. Oxygen, being the second most electronegative atom, has an unbelievable ability to pull electrons away from the iron. And when it does so, the oxygen will become charged, and we know that it likes to gain 2. Its electron configuration, if you want to use 2-6 or 1s2, 2s2, 2p4, and you should have learned that that valence electron shell, holds 6, and it needs 2 more to be as stable as neon in its row. So this loves to gain 2 electrons, become 2-8 or 1s2, 2s2, 2p6. So it makes sense, and you've discussed this already. Redox reactions are really a review of ionic compounds, and the oxygen, being the nonmetal, is gaining electrons from the metal. Metal loses, nonmetal gains. The classic, definition or thing I've been using in class is me and my 3-year-old now, we're being a tug of war, and before I leave for work every morning, what do I say? I say that to feel like a man, I have a tug of war with my 3-year-old. This is the rope, which is really the valence electrons. And of course, me being so much stronger, I'm a tough guy, I pull the rope away from my young son, and of course he's acting like the metal, because he is losing electrons, and I'm acting like the nonmetal. And the reason why I've kept telling you this story is to remember there's a transfer of electrons here, and this transfer of electrons is what causes electrons to be transferred, and of course it's the reason for these redox reactions, which are reactions where electrons are moved from the metal to the nonmetal. But we're going to be more specific in terms of what we call this transfer. We're going to say that the loss of electrons by the metal is called oxidation, and the gaining of electrons we're going to say is reduction. Now, it bothers some people because they say, well, you're gaining electrons, these guys are gaining oxygen, become O negative 2, and the metal is losing. How can reduction be gaining? Reduction's losing. Well, if you think with me, if you're going to gain negative charges, then that means your overall state is going to get more negative. So your oxidation number, the charge you have, drops. So my friends, in chemistry, this oxygen has a charge of 0. We've learned that atoms have a charge of 0. Their protons equal their electrons, right? If you look at oxygen on the periodic table, atomic number 8, okay, and we'll use a very common isotope of oxygen, 16, and we said that this number is the proton number, but it's also the what? The electron number when it's an atom. Atoms equal neutral. So anytime you see a standalone element, I mean standalone means it doesn't bond anything, it has to have a charge of 0. So if I look back here and clean this up here, okay, the iron has a 0 and the oxygen have a 0. They're both standalone elements. Now I know the oxygen is bonding with itself, it's diatomic, it's got that double bond. However, it's still a group of the same type of atoms. That's why it's called an element, and yet we still make it a 0 because it's in its elemental state. All the protons equal the electrons. Now what happens? Well, clearly there's a transfer of electrons. Iron gave its electrons, or probably specifically oxygen being so electronegative, yanked the electrons away from the iron. It was pretty willing to give them up. Iron, in this case, let's say becomes +2. And of course oxygen is -2, and what we're going to make is we're going to make iron 2 oxide. Okay, not the most common of all the rusts, and of course I use the word rust to show that's the corroded form of iron. So this iron 2 oxide. Now I said iron 2 oxide, well, because it's +2. All right, so very simply, what we need to do when we look at redox reactions, before we get into the details of who got oxidized, who got reduced, and that's something we want to look in large quantities, we have to evaluate the oxidation numbers. The reason we have to learn to assign oxidation numbers is so that we can see who got oxidized and who got reduced. So we start with iron. It's got 0. Oxygen's got 0. Okay? And we're going to make iron 2 oxide. Well, in a compound, the whole thing has to be 0, but the nonmetal is -2, and this one is +2. That's the iron 2 part. Okay, in truth, we need to balance this, and there's our entire synthesis reaction, which for the most part, synthesis and decomposition are examples of redox reactions. So in any case, the first skill is assigning the oxidation numbers that we did here and here to be able to identify who actually got oxidized, who had their charge go up by losing electrons, notice it's the metal, and who got reduced, whose charge was lowered by gaining electrons, and of course that's the nonmetal in this case. Now it's not always going to be as cut and dry as that. Now we have a couple of we have a little mnemonic that's very famous, and it's Leo the lion says grr. Losing electrons is oxidation. Gaining electrons is reduction. So we'll get back to that. But the first step in the process is to assign oxidation numbers so that we can see who specifically and who is gaining and who is losing, and that's something that we want to keep track of in these reactions. So let's go to the worksheet I have opened here, and I'm going to assign oxidation numbers. So here we go. Now let's look at these compounds. Looking at each compound, what we want to do is assign a charge. We kind of done this already when we were building chemical formulas or trying to name chemical formulas. Any case, so what I taught you early on is split the compound in half. The one in front usually becomes positive. Notice that's the metal. The one in back becomes negative. So in any case, you might say, okay, what do I do here? I know this thing has to equal 0. So I need to know what the charges are on these compounds. That's essentially what we're trying to do here. What are the charges on each of these individual elements in the compound? So I know that tin has to be positive. That's tin, by the way, stannum. And chlorine has to be negative. So a key would be to go to the periodic table. Opening up the periodic table, I'm going to look for SN. Okay, it's right here. Let's zoom in. Now I'm using a New York State Regents reference table that gives a lot of information. Maybe you do not have the same one if you're coming in from a different place. But tin has, stannum here, has two very simple oxidation states, +2 or +4. Okay, now that's problematic because which one do I pick? So tin is positive, so chlorine has to be negative, but darn it, I have two of these. Well, looking at chlorine, oh my gosh, it's got a bunch also. So how do I know? How do I know which one to pick? There's a very general rule here, guys. You always have to start with the element that you definitely know its oxidation number. Now you may say, Mr. Gradsky, tin and chlorine both have multiples, so it's almost impossible to know where to start. Well, tin has to be positive. It's the metal losing electrons. It's the one that is oxidizing. Well, my friend, chlorine has to gain electrons. It only has one negative choice. In fact, if you look very carefully, all of the halogens only have one negative choice. So my starting point is chlorine with the -1. So right away I know chlorine gets that -1. It's only got one negative choice. It has to be negative. Okay, someone had to gain and get reduced, and someone had to lose electrons and become positive and get oxidized. So because it's -1 and there's two chlorines, the overall charge, I do individual charge up top. Okay, individual charge I put up top, and I do the overall on the bottom. So the overall here is -2 because there are, you got it, two of these. Okay, so it's -2 overall, and well, this thing has to equal 0, so clearly the tin has to be +2. And because there's only one tin, it's +2 individually. So the individual oxidation states of tin and chlorine in tin 2 chloride, remember it's tin Roman numeral 2 chloride, to use the IUPAC naming system, because there are a charge of +2 here. So tin 2 chloride. All right. And the individual oxidation states are +2 for the tin, -1. These overall numbers I use to get the individuals, or after the individual charges, because again, we're after the idea or after the concept or the information in regards to who specifically gained and lost electrons. Okay, let's go on to the next one. Okay, so I've got my lead chloride again. And again, I can start with, well, okay, lead and chlorine. Well, lead has a bunch of oxidation states, as you're going to see. Actually has two, +2, +4, just like tin. It's in the same family or same group, so notice it has very similar characteristics electronically anyway. So +2, +4, and of course chlorine, same idea, -1. So our starting point is going to be, okay, the chlorine. Okay, no problems here. -1. This case, there's 4 of them, so the overall charge is -4. This has to equal 0, so lead has to be +4 overall. Since there's only one lead, +4 individually. And the name of this, of course, is lead 4 chloride for the +4. Okay, pretty simple stuff. If you like your positive, negative numbers, that's what a lot of this unit is. Okay, back to this. -1 individually, because it's only got one negative choice. The tin in front has to be positive. This is -4 overall. This has to equal 0, so +4. And this is, well, guess what? +4 overall. And that's, again, these are the numbers we care about. Moving on, lead has to be positive. I know it has two choices, but chlorine only has one negative choice. That's my starting point, -1 individually. There's 2 chlorines, so -2 overall. This has to equal 0. So this is +2 I'm sorry, -2 overall. This has to be +2, okay? And because there's only one lead, +2 overall. Okay, my starting point was the chlorine in all of these problems because that was the one I definitely knew. Okay, now, next one. Okay, the permanganate ion. Okay, this ion, okay, is -1. This is a polyatomic ion. So it's not going to equal 0, it's going to equal -1. But everything else is the same. I've got my manganate, and manganese I should say, and I have the oxygen here. So I go to my periodic table as my guide. Okay, I look at my nonmetal, it's a -2 for oxygen. Okay, now you see -2 because that is the most common oxidation number. There are a couple of others they do not print in this type of a reference table because of the exceptions that are far and few between. But 99% of the time, oxygen is -2. Okay, let's go to our transitional element way over here and look at the different choices this manganese has. +2, +3, +4, +7. How do I know which one to pick? My starting point is the one I definitely know. And I know definitely that oxygen is -2 here. So I continue on, and it's -2. All right, let's make this -2. There's 4 of them, so 4 times 2, -8 overall. What charge do I need for the manganese in order for this to equal not 0 like we did before because these were compounds, but -1? Yeah, clearly +7. And because there's only one manganese, it's +7 individually. As you can see, this is an easy scale, but very important. Okay, now we're upping the ante. We changed the charge here, but now we're bringing into a ternary compound, more than 2 elements involved. So here, what I do here is, normally, it's the one in the middle that has multiples. So the bookends are the ones we usually know. And nothing's always perfect, but just as I talked about before, oxygen is always -2. There's 4 of them, so 4 times -2 is -8. And, well, zinc. What charge in zinc does sulfur have? I mean, we have sulfur and zinc left. Now, usually it's the bookends, okay? But just to show you, let's go to the periodic table, and that's our friend here. We go to sulfur. Sulfur is a negative and or positive. They may say, Mr. Grotsky, it's a non-metal, so I can just pick -2, all right, just like chlorine. Well, no, if the element's in the middle, okay, normally it's usually some positive charge. So don't always think that non-metals will be negative, okay? Most of the time they are, and that's why they see this -2. But there are some occasions where they could be positive, and this is an example of one of them, okay? So zinc, look at here, only has one choice, it's +2. That +2 for zinc that I definitely know, and the oxygen that's -2 I definitely know, will lead me to the element that has multiple charges. In the other problems, we only had 2 compounds, 2 elements, it was binary. The one that we definitely knew, got us to the, help us figure out the element that we did know that had multiples. So in this case, we're going to start with the 2 out of the 3 that we definitely know. Oxygen is -2, and zinc is +2. So those are the ones we definitely know. It's the only way this could be done, because if you had 2 out of the 3 that had multiples, you couldn't answer this. So when it's binary, 1 out of the 2 had to be definitely known, and the one we just did previously was oxygen, and the other ones that were definite, okay, was the chlorine. It only had one negative charge. The other one was positive, so it had to be -1. Okay, same idea here, but now we've got 2 that are definite. That's the only way to answer this. The 2 that are definite to answer the third that has multiples. So zinc is only +2. There's only one zinc, so it's +2 overall. This has to equal 0. So obviously in this case, -8 plus 2 plus what number is 0? And you would say +6. Okay, I should say +4. Okay, all right, so bad Grotsky there. No, it's +6. What am I talking about? 6 plus 2 is 8. So +6 and +6. Okay, and the reason why I do +6 is only one sulfur. All right, and Mr. Grotsky, why are you always doing that? Well, because look at the case that we get to number, let's say, 10. Let's just jump to 10 for a second. Okay. Oxygen, you've guessed it, is -2. Only one choice. That's the most prominent. Okay. 7 times -2 is -14. These have to equal 0. Hey, potassium's a group 1 ion. It only has one choice, +1. There's 2 of them, +2 altogether. What's the total charge I need for chromium? When added to +2 and -14, that gives me 0. Okay, and that'd be -12. +12. I had a tough time this morning. Okay, so +12 and a 2 gives me 14. Now, the reason I'm showing you this is that it's not always going to be the same element. +6 to a +6 up top. Okay, so +12, my friends, here is for both the total amount of chromium. So what's the charge per each chromium? Yes, +6. Okay, and that's how it's done. So yeah, these are the overall charges, and these are the individual. Just complete the ditto. Okay, these are standalone elements, so what charges do they get? Protons always equal electrons in an atom, whether it's monoatomic or diatomic. These are zeros. Last one, last couple here. Oh, and by the way, yeah, let's do this one. Let's do this one a little differently. Let's break this apart. This is the sulfite ion in table E. Same properties, except in table E, this is -2. So I'm going to do it this way just for a little bit of fun. Okay, maybe not so. Okay, 3 times -2. So this oxygen is -2 individually. This is the total charge. Let's get that out of the way. I rewrote it over here. It has to equal that. 3 times 2 is -6. This has to be +4 for the sulfur in order for this to equal -2. Okay, so I could have started it that way if I wanted to. And if you notice, if this is +4 and this is -2, okay, or this whole thing, I should say, is -2, you would need each sodium to be +1 apiece. So that you could look at them many different ways. So I'm going to go back and do it like I normally would. -2, -6 overall. Sulfur has multiples. Group 1 ion is +1 individually only, always. There's 2 of them, +2 overall. What number for sulfur do I need to equal 0? So that a -6 and a +2 give me 0. Let's see if Grotsky can do this today. Yes, +4 overall, but since there's only one sulfur, it's +4 individually. Okay, let's do another. Look at H. You may say, Mr. Grotsky, H is +1. Not always. H, if you check out your periodic table, can be +1 or -1. So if you've got a group 1 ion that's +1, it tells me when the hydrogen is -1. So this is potassium hydride. Okay, and hydrogen is normally +1 with the exception when you have a group 1 ion. Has to be +1, so it tells me that this one is -1. Now, oxygen, and this is in one of the exceptions to oxygen, oxygen is normally -2. So if you were to throw a -2 here and just go on your business like you've always been doing, -2 times -2 is -4. This has to be +4, and you get an oxidation state of +2 apiece for hydrogen, which does not make any sense. So there's something wrong here. Yes, in a peroxide, which is an extra oxygen in an organic compound, oxygen is actually -1. Now, you don't have to memorize that. You can figure it out because if you put a -2 here, that wouldn't make any sense. H in front denotes that H is +1. Okay, normally. 2 of them is +2. So oxygen had to be -2 overall. And because there's 2 of them, each one is -1. So there's a case where oxygen is -1. There's also a case where oxygen can be positive. Look at this. These are exceptions to the rule. Oxygen is almost always -2. So fluorine only has one choice, -1, -2 overall. You've guessed it, oxygen is +2 in this scenario. So these are the exceptions to oxygen that could pop up, but almost Always, besides those two exceptions, oxygen is its -2 form. Okay, hope that helped. That's the first skill in redox or electrochemistry.